data set, and it may be only few items, elements of data set, that are many standard deviation away from the mean. So the distance between these elements of data set is more than one standard deviation. If we have n data items and standard deviation which is equal to sigma, I told you that ordinary designation of standard deviation is sigma, small sigma. We have n data items and standard deviation sigma. There are at most 1 divided by k squared data points lying k or more standard deviations away from the mean. And here, this is not number of data points. This is a fraction. This is a part of the data set. For example, let's consider data set with n elements and the standard deviation sigma, and analyze how many items or elements of data set lie 2 or more standard deviations away from the mean. 2 or more standard deviation. K will be equal to 2, k squared is equal to 4, 1 by 4 is equal a quarter of data points at maximum may be 2 standard deviation or more away from the mean. This is the sense of this property of standard deviation. And if you remember, we finish it on this slide. I break here my lecture and ask you, do you have any questions or comments concerning previous lecture or maybe material of this lecture? Did you read something from the textbook concerning previous lecture? Maybe somebody? Well, it is not necessary, but it will be better for understanding our learning course if you read the textbook, because this presentation is only part of the material, only main formulations and examples are considered here. Some details you can add to your understanding when you read the textbook. Well, no questions, no answers. We'll continue considering different numerical characteristics of one-dimensional data sets. Every one-dimensional data set may be represented on the straight line, the numerical straight line. And it is maybe main feature, main characteristics of one-dimensional data items. And all the characteristics which we consider in this part, in this chapter, are oriented to analysis of one-dimensional data items. Mean, standard deviation, and then variance. The third characteristics, very important, very applicable characteristics of one-dimensional data, and not only one-dimensional, but about more dimensions we will tell on the future lectures. The definition of variance. for data set with n elements, the variance is sum of squares of differences between elements of data set and mean. So this is a square of standard deviation. And in theory of probabilities, in mathematical statistics, in data science, the both characteristics are used. Standard deviation and variance. Square of standard deviation is equal to variance. These two characteristics represents the numerical values different scales. The scale of standard deviation is the same than scale of the data. If the data is represented in dollars, the standard deviation is represented in dollars as well. But variance will be represented in square of dollars. And we should understand that these two characteristics of distribution of elements of data set around the mean, these two characteristics are different scale characteristics. How to understand, how to think about the variance? If you substitute elements of data set by mean value, you will have an error after substitution. And we will think about the variance as the mean square error you would incur if you replaced each data item with the mean. This is an explanation for understanding of these numerical characteristics, variance. And another connection with previous material, then this is a square of the standard deviation. And this so important characteristics has some properties, only two of them. When we translate the data, variance does not change, not changed. And when we multiply each element of data set by the same value k, the variance will be multiplied by k square. Because we have this expression with square. The proof of these two properties are so simple, and you have an opportunity to learn these proofs in the textbook. One more very interesting and important characteristics of one-dimensional data sets is the median. The median. Let's go back to the example with bar visitors and net worth of them. Do you know who is Warren Buffett or Bill Gates? Maybe yes. Or your favorite billionaire. Let's consider the situation when a billionaire added to these 10 visitors. What happened to the average net worth? We had only 10 visitors, and now we have 11 with Bill Gates. And how to calculate the mean? We had the mean for 10 visitors as $107, you remember. Multiply by 10 plus 1 billion from the Bill Gates. The average characteristics changed significantly from 107 to about 100 million, 90 million. Well, this is very important example. If you would like to evaluate the data set in general, from general point of view, we should make a conclusion that the average characteristics changed significantly, but due to only one point, only one element of data set. The billionaire is known as an outlier. What is outlier? Outlier is element of a data set which is situated far from all the elements. The element is not the same, not the similar to the main part of elements. All people have only $100, but one person has 1 billion. And if we represent these items graphically, we will receive the picture. All the points near $100 and one point is far from all the points. And maybe average characteristics, the mean, proposes us not very good description of the data set, of the whole data set in general. The median is an alternative to evaluate the average characteristics. What does it mean, median? The median of a set of data points is obtained by sorting the data points and finding the point halfway along the list, halfway in the middle of the data set, middle element of the ordered data set. This is designation of median, and some very simple examples. The median of this data set with 3 elements is the middle element. Here, 5 elements and the middle element as well. Here we have even number of elements. We should take these 2 elements and calculate the mean between them. 4 plus 5 divided by 2. This is a median of data set with 4 elements. And let's come back to the example with net worth. The median for 10 people was $107. If we insert the billionaire, the median becomes $108. Why? Let's come back to the table. Maybe we should, to construct the median, we should order this table, but $108 is the element of the list. And for these 10 items, we should order these elements by increasing from this one till to this, to 124, and we should calculate sum of 5th and 6th ordered elements and divide by 2. When we add the billionaire here with maximal sum of money, and order these numbers, we should have the sixth element of the list, ordered list, and the median will be equal to $108. So, adding of one outlier does not change the average situation when we consider the situation from the point of view median. But if we consider the same data set using mean, then we will change our understanding of average characteristics significantly. And this is a reason to consider the data set from different points of view and different understanding average characteristics. The median and the mean are two different average characteristics of one-dimensional data set. And we should think about the median as a middle or center value of data set. The median has some properties similar to appropriate properties of other numerical characteristics, mean, variance, and standard deviation. Please, questions? No questions. Please.
No.
No questions. Well, let's continue. Very interesting, very useful numerical characteristics, but maybe not so simple, but understandable, is entitled interquartile range. Interquartile range. To introduce these characteristics, we should start from other numerical characteristics, percentile. The case percentile is the value such that k% of the data set is less or equal that value. For example, we consider your students group and your points, your grades in theory of probabilities from, for example, from 60 till to 100. And for example, we would like to analyze which percent of how many people, how many students from your group has grades less or equal 90. That value is equal to 90 points, 90. Which percent of the student have your grades on theory of probabilities less than or equal than 90? For example, 10%. Other students will have 90 plus. This is a characteristics of data set. Percent or number percent of the data which is less or equal than a fixed value. And to write this case percentile, we will use such designation, the data set and the k number of percents. For some fixed k, we will consider special values, special percentiles. They have special title quartiles. Quartiles. The first quartile of data is a value such that 25% of the data is less than or equal that value. So, considering analyzing the data set, we should find the value of data item for which the 25% of this data set have a characteristic less or equal that value. And it will be first quartile. The second quartile is a 50%. And the third is 75% of the data. The idea is the same. We should find three values of our data items for which these three characteristics will be calculated. And these three quartiles, in fact, these three quartiles split the data set into 4 parts. Each part contains a quarter of elements based on the divided into percents. First 25% less than first quartile. The second 25% are between the first quartile and second, and so on. We have 3 points which divide the data set in these 4 quarters. These 4 quarters. And let's continue. What does it mean, interquartile range? The difference between third quartile and first. And the sense of these characteristics is representing of interval of the data, which contains half of items, because 75 minus 25, we have 50%. We will consider some examples today later. I tried to explain you this, the sense of these characteristics, and the comment. You can think of the interquartile range of a dataset as an estimate of the scale of the difference from the mean. The mean is a point, is a scalar value, but interquartile range is or represents interval which contains a significant part of the data set. Let's continue. We considered today and on the previous lecture, we considered some different types of data. And we considered categorical data, then some data should remind you, categorical data, and some examples, ordinal data, which may be ordered, this ordinal data allows to represent the values of the data in a special order. For example, small, average, large, or good, bad, and something between good and bad, and so on, neutral, and so on. Sometimes we consider it numerical continuous data, which characteristics should be used for different types of data. Let's consider some examples and comments. The statement, the average United States family has 2.6 children. The author of textbooks thinks that reporting about data set with families, the categorical, this is a bad idea, because you may never encounter the value of children as 2.6. For categorical variable, the median value and the interquartile range is better for reporting, because these characteristics have more sense about the analysis of the data set, more sense than the mean. For continuous variables, the mean is reasonable, is a good characteristics, because the value of the item may be equal to any number, any value from the interval. And for example, if you eat, for example, 2.6 kilogram of sugar during a season, it will be normal characteristics of your food and of your personal way of life. Well, and having different tools for analysis of data, we should choose some of them, should select for characterizing categorical variable, ordinal data, continuous variables, taking into account different properties, characteristics, and features of the data. The next step. Let's formulate these statements. Knowing the mean, standard deviation, median, and interquartile range of a data set, this knowing gives us some information about what its histogram might look like. But many different data sets have histograms that have about the same shape. If we make a glance to the both histogram, maybe by eye, we cannot differ these histograms. With different, maybe mean, standard deviation, and some numerical characteristics. If we have a complex data set, it will be so difficult to interpret these histograms alone, having only histogram, because it is hard to compare many histograms by eye. And these are maybe some reasons to consider some other properties, some other approaches for analyzing histograms and representing of the data sets. This is a very typical picture of histogram, or maybe histogram with very large number of bars, will deal with similar shape of histogram during all the learning course. What does it mean, tails of a histogram? The tails are here. These are elements which are significantly larger than mean, like here, or significantly smaller. And the special title for these parts of the histogram is a tails of a histogram. And one more characteristics or concept of mode. This is a value which corresponds to peak of the histogram. Sometimes histogram has only one peak when all the elements have similar properties, similar nature, and most of them are distributed around the maximum, and the number of elements far from this mode decreases towards negative and positive directions. And these parts are called tails. And some properties or types of histograms. A histogram is unimodal if there is only one peak, like this one. Multimodal when the histogram has many peaks. Only two peaks corresponds to bimodal histogram. Histogram with only two peaks. Let's consider some examples. If we consider measuring heights for males and female, and it is understandable that heights are slightly different, and bimodal histogram correspond to heights of females and males, and it is normal that average height of man is larger than average height of woman, and different values of these characteristics may be described by similar bimodal histogram. For example, measuring the weights of dogs for different breeds may be described by multimodal histogram. Small dogs, large dogs, and middle, described as a populations, may be explained or may be described by multimodal histogram. Sometimes histograms may be symmetric or relatively symmetric when the left and right tails are about as long as one another, similar or the same. Right tail and left tail are very similar too. And one more feature for symmetric histograms mode, median, and mean are situated in the same point. This is a important property of symmetric histograms. When we measure weight, height of the people, when we measure for example, prices, maybe not prices, so specific example. When we measure similar characteristics, we have maybe the same part of items in data set which have larger value of characteristics than mean, and the same maybe part of items which have less value of the characteristics. And the symmetry is we have the symmetry based on maybe natural reasons. But sometimes we have no symmetry in dataset histogram. And the special effect, a special type of histogram is called skew. And for this effect, we have two types, left skew and right skew. Here we have left skew at histogram and the characteristics of it. There are few large values, but some very small values that occur with significant frequency. Small part of small values and large part of the large values. This is a left skew histogram. And this symmetric opposite situation with right skew histograms. Small part, small size of the right tail, maybe it is incorrect. Right tail is represented by the long, but long value, but the number of large elements is small in comparison with the number of small elements. And the right skew histogram has such shape. It is important when we analyze the data set to consider symmetry of histogram. One example from your textbook. Histogram on the left picture, histogram of citations for faculty member A. What does it mean, citations? We say about how many times in the different papers the reference, the links to the certain paper was made. For example, I wrote the paper and somebody after that will read the paper and in their papers make a link to my paper. It is called citation. Very good example. For most papers, we have only one citation of other authors, for example, for original paper of somebody. Less times we have two citations, three, and so on. And here we have interval, maybe from 0 to 100. Very frequently we have citation from 0 to maybe 10 or so on, approximately 10 citations. But very few citations, very few articles or papers have about 100 citation. So if the paper has many citations, the paper is good, popular, and the paper is used for scientific work of other authors. This is a histogram like right skew. Another histogram. Birth weights for 45 babies born in Brisbane. Another example, 44 babies born in Brisbane this year. And according to the random reasons, the histogram looks slightly left skewed. These are examples of non-symmetric histograms. Some conclusions or maybe explanation. One way to check for skewness of the histogram is to look at this histogram. Another is to compare mean and median. So not to look to the picture of the histogram, but compare mean and median. Mean, median. Mean, median. Mean and median at the same point. So, having skew histogram, we have different values of median and mean. And this is a reason for conclusion about symmetry of the histogram. For the first citation histogram, this one, the mean is 24 and 7, and the median is 7.5. For the second, this one. For the second, the mean is 24. Sorry, this is not the second. Maybe they have no second picture here. In each case, the mean is a lot bigger than the median. Here, mean is a lot bigger than the median. And starting from that, we should make a conclusion about unsymmetry of the histogram. For much data, the result is larger than about half of the data set and smaller than about half the data set. So if the median is quite small compared to the mean, then there are many small data items and a small number of data items that are large. The right tail is longer, so the histogram is skewed to the right. So we have at least two opportunities: either compare mean and median, or analysis of histograms by I. The next step in data science, in theory of probabilities, in mathematical statistics is very important thing which consists in standardization or normalization the data. I told you, and maybe you know without me, about data preparation, about preparing the data set for the analysis. And many times, many cases in practical activity, when this preparation includes the standardization or normalization of the data. Let's consider these comments. We can make histograms comparable by either estimating the location of the plot on the horizontal axis, and the second possibility, estimating the scale of the plot, location or scale. The location is given by the mean. So when we move histogram to the right side or to the left side, we change only the mean. And the scale is defined by standard deviation. If we make standard deviation larger, then width of the histogram is increases. When we decrease the standard deviation, the width of histogram along the horizontal axis decreases. For large deviation, we have large width of histogram. For small deviation, standard deviation, we have small value of or width of histogram. Having these two characteristics, we have two possibilities or two tools for changing the scale of the data. We can move data changing the mean, and we have a possibility to change width of the histogram by changing the standard deviation. And it is important, and it is very applicable, to normalize the data by subtracting the location of the mean and dividing by the standard deviation. And the result of this procedure is entitled as standard coordinates or standard data set or normalized data set. Very simple expression allows to construct a normalized or standardized data set. When for each element of data set, from each element we subtract the mean and divide by standard deviation. As a result, we have that data set which is represented in standard coordinates. As a result of this procedure, of this transformation, we have properties of normalized data set. The mean is equal to 0. Why? Because we subtract mean from each value of data item. And standard deviation is equal to 1 because we divided by standard deviation. So we um, obtain the data set with mean which is equal to 0 and standard deviation which is equal to 1. And some comments. Let's read the comments. This important fact about the data is that for many kinds of data, histograms of these standard coordinates look the same. Many completely different data sets produce a histogram that in standard coordinates has a very specific appearance. It is symmetric and unimodal, and it looks like a bell. This one. This is representing this one, representing of histogram, which looks like a bell. If there were enough data points in the data set and the histogram boxes were small enough, the histogram would look like the curve in the figure below. This phenomenon is so important that data of this form has a special name. This one. This is a curve for histogram with a very large number of bars. Data is standard normal data when its histogram takes this form, stylized, bell-shaped, plotted above. And many quite different data sets have histograms that are similar to the normal curve. Some things are represented here. These histograms may be considered as histograms which are corresponded to standard normal curve. This shape and this shape with parameters, special parameters, corresponds to histogram and density function in theory of probabilities, which is extremely important. We will consider this normal curve with the properties and different characteristics inside the second part of our learning course. Now we say only about the shape and importance of this type of histograms. And then I hope that we will consider some probabilistic properties which make the histogram, the normal curve, extremely important and applicable in different applications of data science and theory of probabilities. And this standard normal curve is described by this formula. This expression is, I repeat my previous sentences, very important, very applicable in theory of probabilities, in different applications of theory of probabilities, which applications which deal with normal curve, normal distribution, with normalized data, and so on. We should remember this formula. We should remember this definition, because you will use it in your learning of theory of probabilities and in your practical activity in the data science area. and definition of the normal data. Data is normal data. F, when we subtract the mean and divide by standard deviation, it becomes standard normal data. So, standard normal data, I'll come back, have mean in the 0 point and standard deviation which is equal to 1. It is understandable from this picture for me, but not for you, because we should consider some special properties of the normal curve, and after considering these properties, like 6 sigma rule, you will understand that this is a standard normal curve. But if we change the mean, we move this normal curve to right side or left side from this point, after moving, the normal curve will be normal curve as well, but not standard. If we change standard deviation, the normal curve will change the shape. For example, the peak will be increases and the weight will be decreases for smaller standard deviation. For larger standard deviation, we have more tails and peak of this curve decreases, but the curve will be normal curve as well, but with other values of parameters. We will consider these questions in the theory of probabilities. The textbook, which is in the base of our learning course, and many other sources have links to different data sets, and a very large number of data sets have characteristics like standard normal data or normal data, and these examples may be learned and may be analyzed by you. I hope that soon you will have practice on our learning course. And the first, just a moment, I should say some words about properties of normal data. After normalization, the data set, the histogram of the data set will be close to the standard normal curve. This means, among other things, that the data is not significantly skewed, so the histogram will be symmetric or close to symmetric. About 68% of the data will lie within one standard deviation of the mean. One standard deviation. Mean plus one standard deviation, mean minus standard deviation. And inside this interval, the 68% of all data will be placed, will belong to this interval. This is a property of normal data. When we have two steps, two standard deviations left and two standard deviations right, 95% of the data will belong this interval. And if we take 3 standard deviations from the mean to the right and to the left, we have almost all, more than 99% of the data within this interval. And this is specific property of normal data, normal curve, normal distribution. I will continue my sentence about the practice on our learning course. I hope that your practice will be start soon, and you will have sufficient information, sufficient knowledge for trying to make something with a data set. We will discuss this question with Polina Sitnikova, your teacher on practice. But I think that we will propose you to learn the sources of data, to take the data set one dimension, or to take one-dimensional data set, or to take data set and extract from the data set something one-dimensional, and to try to make with it something according to the material of our lectures, to construct histograms or bar charts, to calculate some numerical characteristics, and then to use some more specific tools of graphical representing. We will start considering these questions on the next lecture. Maybe I say some words. We consider some more interesting, more specific tools for graphical representing of one-dimensional data, and we will consider an example of using these graphical tools, adding to the graphical tools some numerical characteristics which we considered today and on the previous lecture, and to try to make a complex analysis of the data set. We will continue our lectures the day after tomorrow, as I remember, and we have 2 lectures. It will be very hard for me to have 2 lectures in one day, but this is a schedule and we should follow the schedule. Let's prepare ourselves to the next lecture. Well, maybe I finish for today. We didn't have a break, so maybe the time of our lecture is almost finished. Do you have some questions or comments? Please, if any.
No.
No. Well, thank you for visiting the lecture. Please register yourself in the DL, and let's continue. Maybe that's all, and I say you goodbye, students.
Goodbye.
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 Thank you. Goodbye.